entropic uncertainty relation. The entropic relation, which is also called the entropic principle, the uncertainty relation, which is also called the uncertainty principle, is a fundamental concept in quantum mechanics. In classical mechanics, the state uniquely determines the physical quantities such as position and momentum. On the other hand, in quantum mechanics, the state does not uniquely determine the physical quantities, and we can only obtain the probability density function of the physical quantities. The uncertainty relation implies that at least one of two physical quantities has a spread graph of a probability density function. In other words, there is a limit to the precision with which two physical quantities can be known simultaneously. And the uncertainty relation can be applied for any two physical quantities, but in this talk, we consider only the relation between position and momentum. In this case, there are several variants of the uncertainty relation, and the most famous version of position momentum uncertainty relation seems to be the Kennard inequality. However, a stronger relation can be obtained by using the entropy. It is called the entropic uncertainty relation. We will see the relation between the entropic uncertainty relation and the Kennard inequality. Okay, and we have discussed the quantum mechanical aspects of the uncertainty relation, but we will turn away from the quantum mechanics and we will observe that the mathematical aspects of the uncertainty relation. First, we see what is uncertainty. It is the unpredictability of the random variable. The random variable is a quantity which depends on random event. If the random variable has many possible values, it is difficult to precise the value. So, in other words, if the random variable has spread graph of the probability density function, then the uncertainty is high. So the uncertainty measures how spread the graph of the probability density function is. It can be represented by using the variance and the standard deviation, which is the root of the variance, and the entropy. And here are three examples of the graph of the probability density functions. In this case, the graph is spread in wide range. So it is difficult to precise the value. So the uncertainty is high. In this case, the graph is concentrated in two places. So we can precise that the random variable is about here or about here. However, it is difficult to precise which value is taken. In this case, the graph is concentrated in only one place. So it has the lowest uncertainty of the three. Next, we see the variance of them. In this case, the expected value is about here. So the random variable likely differs significantly from the expected value. So the variance is high. In this case, the expected value is about here. So the random variable also differs significantly from the expected value. So the variance is also high. In this case, the graph is concentrated in only one place, so the expected value is about here. So the graph is likely close to the expected value. So the variance is low. Next, we see the entropy of them. The entropy is related to the height of the graph. So in this case, the graph is low, so the entropy is high. On the other hand, in these two cases, the graph is high, so the entropy is low. Thus, the entropy may be low even if the variance is high, such as this case. On the other hand, if the entropy is high, then the variance is also high. It is because the entropy bounds the variance from below. We will see it later. Next, we see what is uncertainty relation. For any function psi from R to C, either psi square or psi half square has high uncertainty, where psi square is the abbreviation for psi x squared, and psi hat is the Fourier transform of psi defined as this integration, where this symbol means the integration from minus infinity to infinity. So the uncertainty relation implies that either psi square or psi hat square has a spread graph. In quantum mechanics, we consider that psi is a wave function. Then this function is a probability density function of position, and this function is a probability density function of momentum up to scalar. Then the uncertainty relation implies that at least one of position and momentum has a spread graph of a probability density function. It can be formulated by using the entropy. It is called the entropic uncertainty relation as follows. Suppose psi square is a probability density function. Then the entropy of psi square and the entropy of psi hat square is not less than 1 minus ln2. It is equal to 0.306 blah, 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 where ln2 is the natural logarithm of 2. Here, HF is Shannon's differential entropy, defined as the integration of HFX. And HY is defined as minus y ln y. And here is the graph of the HY. So the entropic uncertainty relation implies that either psi square or psi hat square has high entropy. And by the way, the entropy bounds the variance from below as follows. Suppose f is the probability density function. Then the variance of f is not less than this value, including the entropy of f. Here, Vf is the variance of f defined as this integration, and mu f is the expected value defined as the integration of x fx. So this theorem implies that if the entropy is high, then the variance is also high. By combining this theorem with the entropic uncertainty relation, we can obtain the variance version of the uncertainty relation. In other words, theorems 1 and 2 leads to the variance version of the uncertainty relation. Here is the variance version. Suppose psi square is a probability density function. Then the product of the variance of psi square and the variance of psi hat square is not less than 1 over 16 pi squared. It is equal to 0.00633, blah, blah, blah. So, at least one of two variables is high. So this inequality, in quantum mechanics, this inequality is equivalent to the Kennard inequality. And this inequality appears in much of literature. On the other hand, the entropic uncertainty relation is stronger, but seems to be less known than the variance version. Actually, we can derive from the entropic uncertainty relation that the two graphs are not of this form. However, we cannot derive it from the variance version because the graph of this graph has high variance. So the entropic uncertainty relation may be more valuable than the variance version in some cases. Okay, let me stop the main of this talk and spend the rest of time advertisement. In this talk, we consider the functions only on R, but however, at least part of this argument can be generalized for any locally compact group, such as V groups and compact groups. There are several examples of V groups, such as Rn and special linear groups and finite groups. The finite groups can be regarded as zero-dimensional V groups. I am studying the generalization of these inequalities for locally compact groups. In particular, I am studying Young's convolution inequality. I will explain about this inequality, the generalization of Young's inequality at 15 o'clock in math seminar. And Young's inequality is related to the uncertainty relation indirectly as follows. Young's convolution inequality does not appear the Fourier transform, but it is equivalent partially to the Hausdorff-Young inequality for the Fourier transform. And the Hausdorff-Young inequality is the key of the proof of the entropic uncertainty relation. The Hausdorff-Young inequality and the entropic uncertainty relation can be generalized for any locally compact groups. But for this purpose, it requires many knowledges, such as representation theory and spectral theory and C-star algebra and so on. And many open problems about these inequalities remain. On the other hand, Young's inequality requires relatively little knowledge. So I will explain it at math seminar. Okay, that's all. Thank you for your attention.
Thank you very much. So very nice talk. So questions.
Inequality B rather than that's one. If it is equal, what kind of constraint?
The equality holds if and only if f is the Gaussian function.
Okay, so Kodama-san, you have a question.
It might be the similar question. So the first question is the theorem 1 is strict. I mean, there is a equality. Theorem 1.
Yes. It is also the Gaussian function.
And theorem 2 is.
Yes, it's same.
So finally, the corollary 3 is also equality is true for Gaussian function.
All of them, that equality of all of them only Gaussian function.
Okay, that's it. Thank you very much.
What's the generalization of theorem 1 to Rn?
In the case of Rn, yes, it is the summation of the entropy is n minus 1 minus n in Rn.
N times 1 minus L2. So n times 0.306.
Yes, it's true.
Is there a discrete version of this, or is it mostly continuous?
I don't know, but it may be exist, but I don't know. Sorry.
Excuse me. So, what is the essential origin of the inequality? That is just a function, the form of the function of hy, the form that one, the origin of the inequality.
He means uncertainty.
Yes, and in theorem 1.
Theorem 1.
Yeah. So, and what is the origin of the inequality? Origin. Where does it come from?
I need to develop on this question. What is the physical meaning?
No, and mathematical. Oh, mathematical. Yeah.
Yes. So
The function hy minus y log y. That function is the origin of that inequality.
what is
If it's the Shannon entropy.
Yeah. That is true.
yes.
I'm sorry, in Japanese. その不等式が、結局何から出ているのかということが僕は気になってるんですけど、その関数形が鍵だったんですかってことが気になるんですけど。
それは、そうですね。この関数形が割と鍵になっていて、少なくともその、
hy ってやつですね。
そうです。hy という形が重要になっていて、それはその、さっきちょっと話したんですけど、ハウスドルフ・ヤングの不等式から導く際に、結局、そのハウスドルフ・ヤングっていうのは、簡単に言うと、LP ノルムに関する不等式なんですけど、それの微分をすると、このエントロピーの形が出てきて、ちょうど、これの Y の P 乗みたいなものを微分することによって、これの、本当はここに肩に係数がつくんですけど、そういったものが出てくるっていう。
Thank you. So in that sense, from your generalized theorem, you can derive that form naturally. Oh, interesting. Thank you.
This is attempt I think, for details.
I think it's very best question. So entropy for phi and phi tilde are different.
Entropy of.
Yeah, it's
They
different.
are different. So I completely split physical system. So why just different bases for why they are different? That's
Because if you're in the eigenbasis in position space, it's flat in momentum basis.
yeah, I know, but the entropy is like a physical quantity.
No, entropy is completely different. For one, it's 0. For the other, it's infinity.
Yeah, but I think the question, what is the physical meaning? I get back to the question. What is the physical meaning of entropy?
Like a state, right? To have a last state entropy is a lot. But I mean, you can use a physical quantity, so it should be.
But the observable is different. One is x, the other is p.
Yeah, but its physical quantity is to be, the basis independent.
Well, usually in thermodynamics class, we consider phase space where x and p both can be fixed. But this case, we consider quantum system state then we choose either X or P for the system.
So you choose X like it's a condensation basis, the quantum basis.
You think it's not quantum
It's
class?
eigenstate.
So this is, you're talking about like trace of row log row, then it's basis independent. But this
Yes,
is not,
yes, that's
this is not trace, this is class, not an object. That's fine. It's not trace row log row, it's literally the integral of P of P.
So this is not entropy. This is
So if you take your state, you can only minus the speed of D0, you have this region on D0, because there are basis. Yeah. Okay, you can use motion.
So it's basis, depend on basis. Choose.
it's not really the entropy. It's not really the entropy.
But can you give a meaning? Because the inequality on the variance has a clear physical interpretation, right? You said it's like I cannot arbitrarily know the position and the momentum.
Yes.
Can you give some degree of meaning to the entropy in theorem 1?
Yes.
Yes.
Do you mean the more variant of the position and expected the position and momentum?
I don't know. Like for the variance, it's clear, but for this, I don't know if you can.
I would say that's not true. I don't think that's true.
But it doesn't have a.
No, it has a physical meaning. It doesn't quite have a physical meaning. You want to give it, well, no, I don't think it works nicely for Gaussians and if you've got a single.
Okay,
but the variance gives far too much weight to the case of the distribution. It's not.
Is related to your question.
Yeah, but okay, but
Finite.
there's a certain degree of
system.
I think it's completely different. What he's talking about is if it's because for pure state, the entropy he's talking about is always the trace roll out roll. This is a way.
What about psi of psi cube or psi? I mean, if you have a higher power or lower power, what happens? The same. You have a bound. You should have a bound. Instead of the psi square, you can choose any power, right? Then why you chose psi square? Maybe it's related to the variance or but.
Yes.
Entropy consultant deviation itself may be valid for all powers.
I only know that power is only 2. So I don't know about entropic uncertainty relation can be generalized for the power is changed version. So I only know only square version.
Could you explain what do you mean by the entropic uncertainty relation is stronger? Stronger means, for example, in the ordinary variance uncertain relation prohibited, but still allowed by this entropic uncertainty relation, or what do you mean by stronger?
First, the variance version can be obtained by using the entropic uncertainty relation. So the variance version is contained in the entropic uncertainty relation.
No. Therefore, my question is that if something is prohibited by variance version, but still allowed by entropic relation, or what do you mean? Stronger.
Yes, it is. There is examples of this graph, such as this graph. So the in this case, the variance is high and the entropy is low. So the in this case, the and so sorry, I'm sorry, I cannot answer this question. So I'm sorry, actually, I don't know. Sorry.
I see. Oh, it's okay.
All right, so maybe you have a lot of questions, but maybe you can ask in the seminar later. And thank you very much for the great talk. And
Right. そうですね。だから